Okay, so welcome everybody to today's co-working seminar. Our speaker is Veronika Pillwein, and she will be talking about proving positivity for P-recursive sequences.
Okay, thank you. Yeah, thanks for the opportunity to speak here. It's been a while that I've been giving a talk, so if I'm too fast or too slow, or there's any question, please feel free to interrupt me at any point and ask questions. Okay, so I want to talk about proving positivity for P-recursive sequences. So let's start by, even though from what I saw from the audience, most people will know by defining what is a P-recursive sequence. So the sequences that we are looking at are, I'm always working over a computable field, and I call a sequence P-recursive, also holonomic or P-finite, if it satisfies a linear recurrence with polynomial coefficient. So the very simple, very famous examples are the Fibonacci numbers that most likely everybody knows. And in this case, the polynomials are actually constants. And in this case, if the recurrence is linear with all constant coefficients, I will also call it C-recursive. Then an example for a P-recursive sequence, also very well known, harmonic number satisfying also a second order recurrence, this time with polynomial coefficients, all degree 1. Yeah, it's like this. And another sequence that will appear later in this talk that introduces yet another parameter, dx, are orthogonal polynomials, the Legendre polynomials that are L2 orthogonal on the interval -1, 1, and they satisfy this kind of recurrence relation. So all these are feasible inputs for the algorithms and methods. Well, not all of them are feasible for all the algorithms that I'm discussing, but for most of the algorithms, this will be a feasible input, something like this. Holonomic P-recursive, C-recursive sequences are nice because of many, they have this nice finite representation, but also they are closed under many operations. So if I add two P-recursive sequences, they are P-recursive again. If I multiply them, if I take the Cauchy product, if I shift so many operations, I stay within the class of P-recursive, and also for C-recursive, I stay within the class of C-recursive sequences.
Excuse me.
In
the Legendre polynomial, we have an x in the coefficient. So I thought it says polynomial. Oh, in kx. Okay, sorry. Right.
Yes. So yeah. So this is a sequence in n and of polynomials in x. Yeah.
Right. Okay. Thank you.
Yes. Thank you. Okay. So now let me get to the positivity problem that is the topic of today. So given a sequence satisfying a linear recurrence, I want to prove that this sequence is positive for all n in n. And this is the simplest way of stating it, but I will also, if I consider non-negativity, I will still call it the positivity problem because it works, it can be solved with the same methods. And the positivity problem, it also, if I, from what I said before, if I take linear combinations of P-recursive sequences, they are P-recursive again. So if I want to show that one sequence is bound by another sequence, I can show that the difference is positive. So it also falls under this class of problems. If I want to show that a sequence is non-zero, for instance, then I could show that the sequence squared, which would again be P-recursive, is greater than 0 for all n. And this latter example already indicates how difficult this problem is in general, because the problem for showing that, yeah?
Sorry, just now, I think the x should be an n. Is that right?
Here?
Okay.
Or here? Here, this x?
Yeah. In the second coefficient, 2n plus 3 times x, the x should be an n?
No, this x is supposed to be an x. So it's the Legendre polynomials, the orthogonal polynomials, and each polynomial Pn is of degree n. So, and this x gives the rising of the coefficient, the coefficient.
Okay,
so
okay. All right, I misunderstand the.
So this is really, it's. We will talk about it as a sequence in N and view the X sort of as a parameter, but the X is meant to be there. Yeah, it's an X.
It is an X. Okay. How does it?
Okay. So this is then the field would be K of rational functions in X, say.
Yeah, but the little p. So what is the little p in here?
This P here. So it starts
the
with
small. No, the lowercase p.
Lowercase up here. This is here. This lowercase p.
Yeah. Yeah.
These are the polynomial coefficients in the recurrence. So here would be p2 would be n plus 2. P1 would be minus 2n plus 3 times x, and P0 would be n plus 1. So this would be the three coefficients in the recurrence.
But I thought in your definition, you substitute n for the x. Is that right?
No. The x is an x. It's a parameter that is there. So it's all the Legendre polynomials are a sequence of polynomials in x.
Yeah, maybe just to clarify. So the x in the definition of holonomic is maybe not the same x as the x in the definition.
X here. No. Yeah, this is just, sorry, this x. Oh, this caused the confusion. I'm sorry. Yeah. So this is not, this is just the polynomials. Yeah.
All right. Okay.
Thank you. Thank you.
Thanks.
I will look at that. Okay. So, yes, I was about to say, so this is the problem of deciding positivity is a difficult problem in general. So if I restrict the class of the input class to C finite or C recursive only, then even there, this positivity problem is known to be decidable only for sequences of small order. And this is because in part of, if you think of the Skolem problem that I just started mentioning, that decides whether a C finite sequence has a zero, and this is notoriously difficult already. And this is, as I said, the positivity problem. If I can decide the positivity problem, I can decide if a sequence has a zero, because I can show if it is greater, the squared sequence is greater than zero. So it is difficult, and I'm mentioning some results that up to order 5 that are known, and Orgnin and Borel are in particular very active in this subject. They also looked into p-finite sequences where there is much less known and only for restricted classes. So there's this paper that I have here that is very recent. Then even more recent is work by Ala Ibrahim and Bruno Salvi. So there's the first one is a paper from some proceedings from 2 years ago. Second one is a preprint. And there's also a paper by Ala Ibrahim that has been recently accepted at ESAC. So she will talk about this at ESAC 2025 if you go there. So go and listen to the talk. I will talk a little bit how this relates to the things that we have been doing in RISC and in Linz. But I will focus more on the things that we have been working with. And this is the so-called Gerald-Kauers method. So this is something that goes back to Stefan Gerald and Manuel Kauers. They introduced this like now 20 years ago, more or less. And it's a method for proving positivity for p-finite sequences that I will introduce next. It's a method that is using cylindrical algebraic decomposition. So I would like to just briefly give an overview of what CAD, cylindrical algebraic decomposition, is used for. So if I am given a polynomial formula, so a formula of the type that we see down here, involving quantifiers, CAD can compute a polynomial formula without quantifiers that is equivalent to the given formula. And in the case there is, if there are free variables, then it will be depend on these free variables. If there are no free variables, then the output will be one of the logical constants, true or false, which is the case that we will be in now. CAD is computationally expensive, and it's a black box. It's not something that has easy, it's something that for humans is easy verifiable why this thing is true or false in the end. So there's no certificate or something like this. There are several implementations the things that I am showing today will be programmed in Mathematica and use the Mathematica implementation of CAD. Okay, so this works for polynomial input as in polynomials here, but not as polynomial sequences of polynomials. So as the type of input that we look at, not for P-recursive sequences. So I want to steal not quite steal, I borrow a slide of Manuel Kauer's. So what if an inequality does not match the required pattern? So as he says, relax, don't panic. You can still apply CAD and in certain cases it helps solving a problem. So the example that he gives here is, I have an inequality, so a formula for all n greater equal 0, show that, greater equal 2, show that this inequality holds. So there are square roots there that are not polynomials. There's a summation sign and there's an integer variable. Yes. So how can we invoke CAD to verify such an inequality? So first of all, the integer variables are considered, are generalized to real variables. The S here is standing for, is a new variable that is introduced for the sum. And then what this formula says is, so I want to prove that for all n greater equal 0, real, not integer now, assuming that this sum is positive and it is greater than square root of n, so I'm doing a proof by induction, then show that the next, so Sn plus 1, so this S plus the next element is satisfying the next inequality. So it's a proof by induction. It is something that is over, all the variables are considered as real variables. So it's a more general formula, but if it is true, then I have proven the formula up in the example, okay? So I think we agree there. It may be false. So this may be false even if the original inequality holds. But if I can prove this, then I have proven the original inequality. And the last thing that is not clear why it can be, there are the square roots, but square roots can be described by algebraic equations, and thus I have the polynomial setting that I need. Okay. Good. So this is the idea that I want to follow for recurrences now. So let me show it for a recurrence of order 2 in more detail, and a recurrence of order r works the same thing. So say I have given a sequence fn through the recurrence relation, and I want to show that it's positive. So I want to do a proof by induction the same way as in the previous slide. And as before, I do a generalization. So I introduce a real variable x for the integer variable n. The y0 corresponds to the fn up here, the y1 to the shifted fn plus 1. Now the assumption is that, so this is, I'm talking about non-negative integers, here non-negative real numbers. I assume that y0 and y1 are greater 0, and then I want to show that fn plus 2 is greater 0, and for this I use the recurrence relation and my new real variables. This is a more general statement, but it is something that I can give to CAD, and if CAD says this is true, then up to initial values, I have proven the initial inequality that I'm interested in on the P-recursive sequence. So this can be cited by quantifier elimination, but as I said in the previous slide also, it may be false even if the sequence is non-negative, because this may not be the way to prove this. There's something that Gerhold and Kauer suggest to do in this case. They say, okay, if the method fails, then add what was the assumption before, so add the positivity of fn plus 2 to the assumptions, shift the recurrence by one more and show that fn plus 3 is greater 0 based on what we know before. So the thing done here is the recurrence applied twice to get to fn plus 3. And this can again be done using CAD. It may still fail, and then they suggest to keep going. So put this with the assumptions and go until either in every step check the initial values, either you find something that is negative, or you can't prove it, or you run out of memory and you don't know what to do. So this is why I call it a method and not an algorithm. In general, it's not clear that this will terminate. And what Manuel and I have been doing at some point is to look into when this terminates for certain particular types of sequences. So our restrictions are sequences with a unique dominant eigenvalue. And we look into balanced recurrences, which means that the trailing and the leading coefficient have the same degree and all other coefficients have lower degree, or at most this degree. And last but not least, that we have generic initial values, so that the initial values lead to a behavior that is related somehow to the eigenvalues of the recurrence. So this is the rough idea of our restrictions. I mentioned before that the work of Ibrahim and Salvi, they consider a similar setting. They, for instance, got rid of our balanced restriction, because they say, okay, which is, they say we can always scale to get to a balanced recurrence. So this balanced is not strictly necessary. The unique dominant eigenvalue is something that is really something that we need, as that's a more strict relation that it's hard to get rid of. So we were able to show termination for certain eigenvalues of the recurrence, but not for the full thing. And Alain and Bruno have been moving on much further than this without using CAD. Still, I will continue talking about this because this has been applied already for many examples. Before showing things that work, I show a simple example where the algorithm fails. So let's look at this. It's a C-finite sequence, and it's very simple. It has eigenvalues 2, 3, and 1. So it has a unique dominant eigenvalue, and it has a general solution that, I mean, for C-finite, we can always find the closed form solution. It has this general solution. So it seems from the solution, it should be very easy to show positivity. But now we want to use really the algorithm. So what does the algorithm do? In the first step, the x now corresponds to the fn, and the y corresponds to the fn plus 1. So we say if fn and fn plus 1 are greater or equal 0, no n involved in this case, then fn plus 2 should be greater or equal 0. And if I take this equation and I rewrite it, this part is greater or equal 0, I end up with y greater or equal 2/5 x. So the blue shaded area is the quadrant, x greater or equal 0, y greater or equal 0, and the red area is the y greater or equal 2/5 of x. So this inequality has a geometric interpretation. So what I want to show is that the blue thing is contained in the red thing, which obviously is not the case. So I follow what Stefan and Manuel said. Let's iterate the procedure, add the restriction to the left side, and go to the next iteration to fn plus 3. So I end up with this red area, and fn plus 3 corresponds to this one, which again is getting smaller. So I'm the left side is certainly not part contained in the right side. And if I keep going, the pattern will just continue. So I'm getting smaller and smaller on the conclusion side, and the hypothesis is always bigger. So this method will never terminate. So this is something I can show non-termination. And in fact, as I said, this sequence is very simple. So if I look at it and I plug in initial values f0 equal 1 and f1 equal 2, I see this is how the sequence looks like. So it's a monotonically increasing sequence, which is easy to show. And this is a monotonically increasing an initial value greater 0. Of course, this gives positivity. So obviously, this sequence is monotonically increasing, and this implies positivity or non-negativity. But not every positive sequence is monotonically increasing. So something that Manuel came up with at some point is, how about trying to make it monotonically increasing? So this is by search simultaneously for a scaling parameter mu greater 0 that makes my sequence monotonically increasing. in a way that I can prove it using the initial Gerhold-Kravers method. So I look for the mu and sum in 0, from where on the sequence is monotonically increasing. So in the end, the scaled sequence is this mu to the minus n times fn, if I proceed like this. And this works in many cases. So this, we also analyze this under the same setting that I described before. And this covers more cases and a lot of cases that the original algorithm doesn't. And for instance, it worked on this, on solving this problem for certain instances, the Gillies-Reznick-Zeilberger rational function. So this is something, it goes back the problem statement to 1983. They defined this rational function, and the problem is, so greater equals 0 means now that all the coefficients in the multivariate expansion are greater equals 0. And it's a very short paper. They came up with this rational function by, they looked into the ASCII-Gaspar rational function. And this is somehow a limiting case of this class of functions. So in the paper, they claim that it suffices to look at the following binomial sum, which is univariate, and this sum is clearly p-recursive. So all that is stated below, not all, those three results are now looking only into this AR of n, the univariate sequence. So in the original paper, they looked at the diagonal and they checked it with a computer for r equals 4 and up to n at most 220. And then Manuel applied the method that I just showed before for the orders 4, 5, and 6 and arbitrary n. And then he stopped there because the computations became prohibitive. And then later, I also applied Manuel's method, but instead of looking for the mu from the sequence that we see here, I looked at the limiting C-finite recurrence, got a guess for the mu, and then only had to prove it. And for me, the bottleneck in the end was not the CD computations, but to get Zeilberger to compute the recurrence relation. So, and then I stopped at r equals 17 because, yeah, at some point you have to stop. You cannot go on forever. You cannot obviously show using this method for all r. It has been proven for all r by Xu in 2019, but as far as I know, this is still just a preprint. So I'm very sure that the paper is correct, but I haven't seen it published yet. And in the 2024 paper of Ibrahim and Salvi that I mentioned before, they also look into this problem and they can also solve it. I think for higher, they use the Maple implementation for Zeilberger's algorithm, and they even go to higher R. So, and apply their method to prove this, and they can show for specific R for all n, they can prove this inequality as well. Yeah, one thing just to mention, Xu does not need the restriction to look at the diagonal. He goes for the whole sequence, for the whole multivariate sequence for cases from r greater equal 8, or yeah, r greater equal 8. So our results are still needed for the lower order cases. Good. So this is a sequence where it doesn't work. Now I would like to go for some examples where it works, but on the way there, I want to introduce a class of sequences and show some other methods that work for these sequences, or other results that have been obtained on the topic of showing positivity. And a very big class of problems that people look a lot in are unimodality and log concavity. So let me recall, a finite sequence is called unimodal. Let me put the picture, if it goes up to a certain point and then it starts going down. So the example we see down there's the binomial coefficient, and it looks very much unimodal. And a sequence is called log concave if this inequality holds, so this, which is also often called the Turan determinant of a sequence. Okay, and in fact, this binomial coefficient is also log concave, and if if I have a positive sequence, then log concavity is stronger than unimodality, and log concavity implies unimodality. Okay. That's the first one. What is a classical result to show log concavity? It's from Newton. If I look at the polynomial, which is like the finite generating function of my sequence, if this only has real roots, then the inequality below here holds, which is, if you rewrite it, a stronger condition, because then you have the log concavity inequality with the number here that is greater than 1. Yeah. So has only roots, then this inequality holds, hence the coefficients are log concave, hence unimodal. And this is something for the rows of Pascal's triangle, since the polynomial, if I plug in d choose n, then I have 1 plus x to the d, and the roots are x equal minus 1, which are clearly real. So this is log concave. Good. Apart from log concave, let's now go to multiple infinite and R-factor log concave. So if I denote the operator that takes my sequence an and goes to this an squared minus an minus 1 times an plus 1, then I will use this notation to denote the corresponding generating function or polynomial. And I call a function m log concave if I apply this operator L time, up to m times, and it's greater or equal to 0 for each of these powers. And it's infinite log concave if it's m log concave for all m. And another thing that is related is the R factor log concave. So if in the log concavity condition, I have a factor R here that, if greater 1, of course, implies log concavity. Okay, if somebody is not familiar with these notations, I can go back to the definition later. So, are the rows and columns of the binomial coefficient infinite log concave? This is something, so up here I drew several iterations. If you look at it and if you compute the numbers, it looks very simple and it looks like the most simple example, and still it took very long to prove that the rows are indeed infinite log concave. And I'm talking about, in particular now, one approach by McNamara and Sagan that tried to get to infinite log concavity through R factor log concavity. So for which R do we have that the R factor log concavity is preserved? So if an is R factor log concave and I apply the operator L and it's again R factor log concave, then it's infinite log concave if R is greater than 1. So we have R factor log concave if for the iterated sequence, so I'm just plugging in the definition. And so they have a paper where they computed this R by hand, but of course, since we have CAD, we can also use CAD to find the optimal R to show that which R preserves this R factor log concavity. So its R has to be at least this 2.61. And by the way, this is the same. So what they had in the paper, it's the same R. So we are not better than, or they were not worse than what CAD says. Okay, this is nice, but it doesn't help for the binomial coefficient. For instance, it helps for some sequences, but not for the binomial coefficient to show infinite log concavity. And the breakthrough in results concerning infinite log concavity, or one breakthrough, was a result by Brandon. That he showed that if the roots of this polynomial that we saw earlier in Newton's result are negative and real, then so are the roots of, if I apply the L operator. And as such, the sequence AN then is infinite log concave. And now, again, if I look at the binomial coefficient, the roots are -1. There's -1 is the only root with a multiplicity d. So all the roots are negative and real. So with this result, we have the infinite log concavity of the rows of the binomial coefficient. Yes. But still, there are many other sequences so this helps in many cases, but there are still other sequences where this is not giving infinite log, even where infinite log concavity is conjectured, but this condition is not applicable. I want to mention another approach by Medina and Straub, that tried to approach the problem from a different point of view, looking at two sequences that are fixed by the L operator. So n choose 2 is a very simple example that is fixed by the L operator. And if you want to see which other sequences, then if you fix a-1 to be 0, which makes sense, then you get the condition that a0 has to be 1, and then they wanted to have something of integer sequences. So if you choose a1 equal an integer greater equal 3, then the sequence that you get is infinite and all terms are positive integers. So these sequences that you see down here, they are all fixed by the operator L, and as such infinite log concave. They have found another example, the coefficient sequence of a generating function of this rational function. So with the parameter k here. And since this is a rational function, it's C-finite, so it satisfies this recurrence. And so this is another example for a coefficient sequence that is fixed by the L operator. They tried also to find sequences that are fixed by L squared. So they came across this example. It's fixed by L squared, but in this case, it's not log concave. But it's holonomic. When they tried to find something that is fixed by L3, they could construct it effectively, but they could not find a holonomic recurrence for these things. Okay. So let me go back to now back to the beginning where I started confusing things. So we are back with the Legendre polynomial. So the Turan, Turan inequality. This is in a sense, log concavity. This is a very classical result. Turan inequality for Legendre polynomials. So here we see the Turan determinant now depending on x, but in terms of n, it's the same inequality. And we see a couple of first cases. So we have the delta 4 is the blue one, then delta 6 is the red, and delta 8 is the orange one. So we see the amplitude is going down. That these things are negative at the site, this is not a mistake. So this is really only holding for x in between -1 and 1, and they're all 0 at x equal -1 and 1. The Legendre polynomials are, they are even for even degree and odd for odd degree. So the Turan determinant, it is this nice symmetric. It's also, what is interesting, if you think, Legendre polynomials are orthogonal polynomials, so they have the polynomial Pn has n real roots, simple roots in the interval -1 and 1, so they are oscillating, but this Turan determinant is not oscillating. It looks very smooth. This keeps going like this. So it's really in this interval -1, 1 and non-negativity, but for instance, I could not prove something like that it's bounded by below by the next I cannot show delta 4 is less or equal delta 6, less or equal delta 8 or something like this, because it's just the opposite. There is, however, a simple scaling that works. So it's something like, if you look at, it's like n times n plus 1 or something of this form. If you put this scaling, then you reverse the order, and then it becomes monotonically increasing with the amplitude, and which is a positive scaling. So there's a proof that exploits this. What I want to talk about now is not that proof, but the original. So it comes from, this is a problem that is around since the early 1900s, if you say, mid 1900s. It was coined by Turan, and Sego in 1948 gave 4 different proofs for it. And since then, there have been many proofs. So people keep trying to prove this in different ways or variations or for other families of orthogonal polynomials. And Sego's one of the 4 proofs. I would like to just give a short sketch of it. So here, this is from the original paper. So this is the recurrence that I had displayed in the beginning. And he finds, so he uses the recurrence relation and plugs it in the Turan determinant. Like this. And then he says, okay, this is a quadratic form and it is positive for a large range of x, so a range of x that is growing with growing n. So n for n to infinity, this value tends to 1. So he shows it for a large portion of the interval, and then he says, okay, for the rest I need something else. And then he uses Mailer's formula and has to do something very messy very messy, very elegant at the points x equal plus minus 1. What I like about this proof is because this is the point of view that we are taking also. So he already said, okay, let's just try plug in the recurrence relation and do something here. Yes. And because this is also what we do if we use the Gerald-Kauers method. And now let me come back to the positivity problem in the beginning. So I said, okay, we have a positivity problem is I have a p-recursive sequence. I want to show an is greater than 0 for all n. And I have the recurrence for the an. And now we have this delta n, which is a combination of Legendre polynomials. I take the product, I shift things, I subtract things. So all these are operations that are living within the holonomic universe. Everything that I do gives me, again, a p-recursive. It shows me that the delta n is also p-recursive. So I have a recurrence. I think in this case, it would be of order 4 or something that is satisfied by delta n. So if I follow the paradigm that I introduced in the very beginning, I would say, okay, I compute this 4th order recurrence, and then I try to show that delta n is greater than 0 using this 4th order recurrence. And I will fail. Because this recurrence is something, so this has not a unique dominant eigenvalue. So there's a problem there, and it's something that also the Ibrahim and Salvi, so this most recent, very interesting papers that I really recommend that you have a look into. They also say this is a restriction that we cannot overcome so easily, and which is also a problem in this case. So they also cannot prove this here. Gerhold and Kauers can prove it, but not because this eigenvalue is not a problem, but because they don't use the recurrence for delta n. They do what Sego already did. So if you have something like this, you are not using the recurrence for the delta n that you can compute, you use the recurrence for the Legendre polynomials. So they set up the this inductive proof that I showed before for sake of simplicity using just the recurrence relation for an. But they use as variables the Pn and the Pn plus 1. And they give this quadratic form, which is really the thing that Sego looked into. They have to iterate the construction 1 time, I think, or 2 times, not very often, in the sense that I said before, if the proof with the induction proof, if it fails, take the conclusion, add it to the hypothesis and shift 1 more. So they have to do this once or so, but then it works. And this is how the input in Manuel's package would look like, where he implemented this method, this Gerald-Kauers method. The package is called SumCracker, and it's available from his webpage, kauers.de. So the command is proof inequality. I'm using here the standard notation for Legendre polynomials. So what you would put here is Legendre P, the name for Legendre polynomials that is used in Mathematica, the built-in name, because he already has you don't have to specify the recurrence relation. The recurrence is, if he sees Legendre P, he uses the recurrence. you say this greater equals 0, you have to specify that the x is between -1 and 1, because as we saw before, this is essential, it doesn't hold otherwise. And this info level is, so the discrete variable is n that we want to do the induction in, and the info level just says that I will see this output that I'm putting here. So it's very fast, it goes brrp, and it says true, and it tells me, okay, I'm extending the induction hypothesis, I'm putting it there, I'm checking the induction step, I'm doing the CD computation, it says true, I'm done. So that's it. It's as easy as that. And yeah, and in general, so if you have something that is combined of different expressions that satisfy recurrence relations, so what it would do is use the separate recurrences for the different sequences and not compute the whole p-recursive recurrence for the object, like here the delta n, but use the individual recurrence relations. So I'm ending with this example if I still have time.
Yeah, that's fine. That's fine.
Okay. So Stefan and Manuel in their paper, they had, when they introduced the method, they showed that, oh, we can do Turing's inequality. And then they said, okay, we can do better. We can, they found that if they add this absolute value, so if you think of this Pn here as the Legendre polynomials, if they add the absolute value of x there, then this is still non-negative, and they proved it using their method. Turing's inequality can be formulated for many other orthogonal polynomials, for instance, Gegenbauer polynomials, which are this Cn lambda that I have here, or another sequence of orthogonal polynomials that are similar to Legendre polynomials in the sense that they are all also even for even degrees, odd for odd degrees, and for a particular choice of lambda, we get back to the Legendre polynomials. They also satisfy Turing's inequality if they are normalized to be 1 at 1. So this is a condition here. So this is why we look at this Pn of x, that is the normalized to be 1 at 1. And what I did together with Geno Nikolov is we proved this inequality for Gegenbauer polynomials. We have two proofs in this paper, a classical proof going over using the roots, exploiting a more classical argument that can also be, that is more Sego style, but they also, this works immediately using Gerald Kauer's method. Turing's inequality also holds for Jacobi polynomials, but Jacobi polynomials, they are now the next generalization. They also defined on -1, 1. They have two parameters and they are no longer symmetric. They also satisfy the classical Turing inequality for certain ranges of parameters alpha and beta, again, when normalized to be 1 at 1. And they appear to satisfy this in this range, this type of inequality, and we give some evidence for it in our paper. But this is something that we could not prove neither using classical nor using computer algebra method. So this is, I'm finishing off with an example that, as far as I know, is still open. So if you want to prove it, please prove it and let me know. And that's all that I have. Thank you.
Okay, great. Yeah, thanks so much, Veronika, for this very nice talk. Do we have any questions or comments? You can just unmute yourself and ask, or if you prefer, you can also just type it in the chat. Okay, let me maybe ask something about about the initial values. So if I understand correctly, so the answer whether or not the sequence is positive, in general, it depends on the initial values, right? And so are there some results of the nature like that the answer is the same for somehow most of the initial values?
So there is a so if it holds for some initial values, then it will hold for a wider range of initial values, I would say. So it's always a domain of initial values that work. And I think that this is something that is also part of what Ala and Bruno have been doing. So that they also consider in their results, they also have the domain where you can start from, where these contracted counts that they use, where they work on. So they have something that is more, it's in general, the approach is more geometric, and I think much more human graspable than the things than just using CAD. And they also shed some light on which initial values work, I believe. Yeah.
Any other questions? So one thing I was also wondering is if you somehow relax the problem by, instead of asking for all the values to be positive, but you only ask for like all but finitely many to be positive, does it become any easier then?
No, but also not more difficult. So this is one of the variations I could have added in the beginning, that if we say we want to know ultimate positivity, I think, then this, I believe that this would not make it easier or more difficult.
Okay. All right, if there's no further questions, then let's thank Veronika again for this very nice talk. And yes, so this was the last talk for this academic year. So we are wishing everyone a enjoyable and productive summer, and we are looking forward to seeing everybody again in fall then, hopefully. All right.